Um, so this is my part one for my two-part video for my IBHL chemistry class. This video I'm gonna talk about the PV equals nRT formula, gas laws, and also we're gonna dive into a big, broad standpoint of what energetics means. And in the next video, I'll go ahead and touch on entropy and spontaneous and unspontaneous reactions, and we're gonna work on the Gibbs-free formula and how to get it, and a little bit of Hess's law, and that's what's going on in this video. Enthalpy. When a substance changes at a constant pressure, enthalpy tells you how much heat and work is added or removed from the system. Enthalpy is similar to energy, but not the same. When a substance shrinks, energy is released, but when it grows or shrinks, energy is used up or released. So when it says used up or released, it's talking about the exo and endothermic values. So if it's being released into the system, it's going to be an exothermic reaction, and if it's being used up, like energy is used, the delta H is used, it's going to be an endothermic reaction. So in order to find enthalpy, you'll need to do E equals PV, which is E is going to stand for the energy, and P is going to stand for pressure and volume, or V is going to stand for volume. So you're going to have to multiply the pressure by its volume in order to get your delta H. And that's the total energy that the system has, and that's in the reaction. Usually the delta H's are given. However, they could be manipulated by a series of calculations, such as Hess's law. Hess's law calculates, and you can find an easier term by using Hess's law. Sometimes they give you averages, and with the average, you can get the delta H is given, and from there you can use the delta H for a number of things, such as using it with entropy and Gibbs-free the formula, because delta H is used in that formula as well. One can easily understand the difference between exo and endothermic. The important difference is that endothermic is going to be a positive sum, and exothermic is always going to be a negative sum. The way I remember is exo means exit, meaning that it's going away, it's being released into the system, while endothermic is absorbing the system, it's positive. You can understand that by seeing what the delta H is. So let's say if a delta H is negative 1,300, you can automatically tell that that reaction is going to be an exothermic reaction, and delta H in the reaction is going to be, let's say 365, it's going to be endothermic because it's a positive reaction, meaning that heat is added to the system. And like this, here's an example problem of what an endothermic reaction would look like. So this right here is an example of an endothermic reaction, and in graph form. So as you can see, there's a lot of activation energy, and there's a lot of absorbed energy, because energy is absorbed, and it takes more activation energy. So what it is, it's entering the system. It's not releasing it, because that's exothermic. It's entering, it's absorbing its surroundings. So heat is added into the reaction, and that's how you can decipher what an endothermic reaction is. Exothermic is, like how I said, exit. It's released into the system, it's released into the surroundings, meaning that it's exiting, meaning that it's a product on this hand, because it's leaving the system, it's being released. Endothermic is a reactant because it's getting absorbed, it's added to the system, while exothermic is a product because it's releasing into the surroundings. And this is what an exothermic reaction would look like in problem wise. So that's an easy way of interpreting what an exo and endothermic reaction is and what's the difference. Endothermic is positive, it's being absorbed. Exothermic is negative, it's being released. This here is an example of an exothermic reaction in graph form. As you can see, it doesn't start as a reactant, but it acts like a product because it's released and it's not absorbed into the system and the surroundings. Oh, there's a lot. An easy way of interpreting what an exo and endothermic reaction is and what's the difference. Endothermic is positive, it's being absorbed. Exothermic is negative, it's being released. Hess's law. So the definition that you get whenever you search up Hess's law is obviously going to be very confusing because it's a medieval man going through serious enlightenment and finding new things about chemistry every single day and make things very complicated for everyone. So this is what the Hess's law definition is, which is Hess's law states that the energy change in an overall chemical reaction is equal to the sum of the energy changes in an individual reactions comprising it. In other words, the enthalpy change of a chemical reaction does not depend on the pathway between the initial and final states. The law is a variation of the first law of thermodynamics and conservation of energy. So obviously it sounds like a headache and people don't really understand it at first glance and become very confused, but the way I remember it is it's the sum of the products minus the sum of all of the reactants is going to be your delta H. And the reason why they do have this new way of to define what is the delta H in a reaction is that sometimes you never know what could happen. There could be a serious explosion, someone can get hurt, so they use the bond enthalpy average and they use it into this formula, in this equation, and get a safer outcome, and it's actually very accurate. And there's also ways where you can get a chemical equation, a balanced equation, and you can manipulate that equation by adding it with other ones, doubling it or flipping it from side to side, and that would actually change the delta H that's given. But I'll go ahead and do some problems and just a few, just so you can understand that how you can interpret Hess's law and how can you notice, okay, this is a Hess's law problem, and I know how to go through it, and I know I'm gonna get the right answer because I understand how to do it. So we'll begin with the actual definition, which is the sum of all the products minus the sum of all the reactants is going to be equal to your delta H, using the averages from the compounds. And yeah, we're going to go ahead and go on paper now. So this is going to be our equation for Hess's law if you're using the standard enthalpy formation, and that's what that is right here. It has standard because it has constant pressure and temperature, and it's most suitable. It's it's like stable state, and it's also an allotrope. So we're gonna go ahead and do one problem on how you can realize that, okay, this is a standard enthalpy formation problem, and I know that I'm gonna have to do the sum of all the products minus the sum of all the reactants in order to get our delta H. All right. So this example problem is going to ask to calculate the standard enthalpy of combustion for the following reaction, which it's asking for the C6H12O6 plus 6O2 yields 6O2 gas plus H2O, and 6 of them. First, before solving a standard enthalpy of combustion problem, you're going to need to figure out what are the values of each compound, because without it you won't get the answer that you need. So Here it's given because it'll always be given. So the C6H12O6 is going to be equal to negative 1,275. Diatomic ions are always going to be 0, and that'll never change. 6O2 is going to be equal to negative 393.5, and liquid water is going to be negative 285.8. All right, so first, in order to solve this equation, we have to denote each coefficient in where it goes, and we understand that in order to get the delta H of this overall equation, the standard enthalpy of this overall equation, we're gonna have to do the products minus the reactants. So the sum of all the products minus the sum of all the reactants. So let's start with the products because we're gonna need to get the products first. So we see that there is 6 CO2s, and a CO2 is equal to negative 393.5. All right, so first we're gonna have to save that. So negative 393.5, and that's going to be our CO2. This is our CO2, and there's six CO2s, meaning that we're gonna have to multiply this this value 6 times because the coefficient is pretty much telling it to. So we can just multiply by 6. All right, and that's our first product. Our second product is going to be 6 liquid water, and liquid water is equal to negative 285.8. So we're gonna go ahead and just put down 285.8. Make sure to know that it's a negative, and there is 6 of them, meaning that we're gonna have to multiply this by 6 times, and this is our H2O. All right, so this is our sum of our products, and we're gonna go ahead and just do it now. So it's 6 times negative 393.5. And that's our answer for the CO2. The water is going to be, so this is our water. So just go ahead and add these two, and that's the sum of our that's the sum of our products. So it's going to be negative 4,700, I don't know, negative 4,075.8. So this is our products. And now we're gonna have to subtract this. Subtract this by our reactants. So going back to the equation, it's gonna be more easier for us because this is always gonna be 0, and anything times that number is just going to be 0 as well. So we'll just leave that blank. But however, our C6H12O6 is going to be equal to negative 1,275. So we won't have to do any further calculations because there's only 1 mole of it. So we'll literally just subtract it by that number, which is 1,275. And we're gonna go ahead and plug this in the calculator. So here, just do this right here. This subtracted by our reactants, which really changes that sign into a plus sign, makes it our delta H be equal to negative 2,000. Our delta H, our standard enthalpy of combustion, is going to be equal, which is here, is going to be equal to negative 2,808. And that's how you do a simple problem of our products minus reactants for Hess's law.